Hello, good afternoon, everybody. Thanks for joining this afternoon for the Flexibility 2.0 workshop. This is demand response and self-consumption based on the prosumer of Europe's low carbon future. So we have 8 very interesting projects today. We'll start off with my quick introduction, and then each project will have about 15 minutes to present their solutions. And if there are any questions, please put them in the question window that you'll see on your right in GoToWebinar. And I'll make sure that that presenter answers your question. So first, we're going to start off with the ebalanceplus project, and that's from Jacobo Escalante from Somoza. And then next we have eDREAM, which is Giuseppe Mastandrea, and Tudor Sierra. Giuseppe is from Energy at Work, and Tudor is from the Technical University of Cluj-Napoca. After that, third up, we have the TABEDE project, presented by Manu Onilon from CSEM. And then we have the Drive project, presented by Alexander Kavskik. Excuse me if I'm butchering your names, from Typhoon. Then we have the HOLISDER project, presented by Arun Submaranian from TNO, followed by the Novice project, presented by Joe Southernwood from IERC. And then AmBIENCe from Jesse Glicker from BPIE, the Buildings Performance Institute of Europe. And then last but certainly not least, we have the Delta project presented by Apostolos Solakis from the Center for Research and Technology in Hellas. So without further ado, let's get to the fun stuff. I will ask everybody except Jacobo to turn off their webcam, please, and mute themselves. Thank you. And I will do the same. So I leave the floor to you, Jacobo. Take it away.
Okay, thank you very much. Let me know when you can see my screen to start.
All set. If you just put it in presenter mode, please.
Yes, let me know when you can see the presenter mode.
All set, but your video seems to not be working.
Okay, it's working now, right?
I see a blank screen. Rachel?
Yeah, we don't see you yet. You can start and I will check what's happening.
But can you see my screen?
Yeah, I see your slides, but not your video.
That's your webcam.
Maybe. Yeah, I'm going to switch off and then switch on. I don't know if it's working.
No, it's not working, but yeah.
No, I'm not sure what's happened.
That's fine. That's fine. No worries. You can just go ahead.
Okay, sorry. Okay, thank you very much for the introduction. The first presentation, my project the name is ebalanceplus. It's about the smart energy flexibility for distribution grids. The aim of the project is to, as you can see here, is to increase the flexibility and the resilience of the energy networks of power system by means of a set of energy balancing algorithms and communication platform that we say as energy balancing platform. And the idea is to integrate different smart equipment that can be production, storage, or different technologies with smart algorithms and prototypes that we will develop in different parts in Europe. Okay, the overview of the project, we are 15 partners. We are carry on the project in 10 different countries. We have 4 real demo sites plus a virtual lab for testing the resilience services, which is related to critical events. And for this reason, we have a virtual lab. We are going to develop 7 core technologies. The project starts on February this year, and we expect to finalize on July 2023. The EU funding is 8 million euros. And you can see here a geographical scope of our project. Femosa is the company I work on, is the coordinator of this proposal. And we are working with different partners in Spain, Portugal, France, UK, Denmark, Germany, Poland, Italy, Greece, and region. So you can see that our scope is very, very European. Also, as this project is related to power system, we are members of the Bridge Horizon 2020 initiative, so we are in contact with most of the projects that are working in smart grid technologies, and with the aim of digitalization of the smart grid and to create innovative solutions regarding generation, storage, and flexibility in the consumption demand side. So we have the opportunity to share our knowledge and to share our innovative solutions with different European countries, that allows us to align our development and results with different European approaches and with different strategy from other projects. So it's a very good opportunity. Okay, sorry. Okay, so I mentioned that we are going to develop several, we say, key technologies are the core technologies that we are going to develop in the project. The first one, this is the most important, that configure our energy balancing platform are the management units. We also have a data exchange middleware in order to communicate different communication protocols and different systems that talks in different languages, communication languages. We have also security and privacy technology to protect from the customer to the DSO premises. We are going to develop new prediction models, of course, in order to deploy this kind of technologies. It's necessary to have better accuracy models for predictions, given that we are going to integrate renewable energy and the behavior of end users. Also are going to develop high efficient power inverters that are based on silicon carbide semiconductor, so the energy efficiency is higher than typical commercial solutions. We are also to develop new vehicle-to-grid infrastructure, especially charging points, and also smart storage for buildings and for district level. What is energy flexibility in our project? According to the International Energy Agency, is the extent to which a power system can modify electricity production or consumption in response to expected variability or otherwise. However, in our approach, the flexibility is dynamic. So in the moment we try to modify this flexibility, the flexibility changes. This is what we say that it's time dependent, and any interaction that and any strategy that we carry out, that we deploy in a power system, the flexibility changes. So it's very important to characterize this flexibility and to identify which are the KPIs and indicators that change this flexibility, and try to predict how this flexibility will change over the time. So it's very important to have, as I say at the beginning, accurate prediction model to estimate this flexibility and to exchange this flexibility in a future market operations that to make sense for customers and for the different electric operators in the network. So in a way that we can guarantee that more flexibility means more benefits and not in the opposite side. This is our approach. It's what we say a fractal-like hierarchical architecture, because our system is composed by different management units that we are going to develop and deploy at different grid levels: customer domain, distribution domain, and transmission domain. So the good point is that each unit manages the energy from this domain to downwards. So in this way, we are following the same structure of the power system or the distribution grid. So our solution is scalable and is replicable in any electric grid network. This hierarchical infrastructure is a bidirectional communication platform in which we can deploy negotiations algorithms between different parts in order to get this energy balancing that we are looking for. For the flexibility management, this unit will address the flexibility management and try to increase this flexibility for building and district using what do we say, flexibility mechanisms. We are going to achieve this release of new flexibility using and connecting to the bags and BEMS using IoT technology inside the buildings. We are going also to deploy batteries, electric batteries, storage system at building and district level. We are also to use and test new power converters in order to create this network and increase the energy efficiency, and also to integrate renewable energy at district level, and also using the potential bidirectional charging points that future vehicles can provide in this extra storage for the grid. We can try to balancing all these elements in our platform. At the left side, you can see the flexibility sources, and the right side, you can see that for flexibility management, we propose management units. These are the units that I have shown you in the scheme, previous scheme, and prediction algorithms, because the negotiations and the different interaction between the management units require these kind of prediction models to make the market we want to build trust and fair for all the players. And in the middle of our approach and what is perform the connectivity between all the parts, we have the middleware. This is a technology that allow us to connect different facilities, different communications system and devices, and also security and privacy modules specific to protect the confidentiality, the privacy, and the security of the different customers. Our platform has, as all the platform, has some advantages and challenges. Regarding advantages, the good point is that allow to deploy local and distributed control algorithms. So this is very flexible in this regard. We can implement local algorithms to manage the energy at building or district level, but also we can deploy distributed control algorithm in which we can interact one unit with other, deploy negotiation algorithms based, for example, in innovative peer-to-peer networks and peer-to-peer markets. Other advantage is the scalability is assured because the architecture is based on the power system. So we can install and we can deploy this system in the future in any existing electric network because it follows the same structure. Our management unit can be physical or virtual. We have a previous project that the name was eBalance. And we have the experience of, in some cases, we need to virtualize. I mean, instead to be physical, we can run only with software and try to perform some kind of communication with the communication system in the network. Also, the platform, as I say in advance, the platform allows deploying innovative market based on flexibility thanks to these negotiation algorithms that we can deploy because the different management units can communicate each other with a hierarchical approach in which the distribution domain rules against to the customer domain. And the good point that we can test bidirectional or unidirectional signal, so we can deploy resilience algorithms for critical events. I mean, in the case where some critical events try to switch off or part of the network is suffering some problem, the different units can request the help to the downwards units in order to balance the energy or to recover the system quickly. However, this system at first it seems very suitable, has some challenges, technical challenges that we are going to address in the project. The bidirectional communication requires a very good network, communication network, so the network stability is can provoke problems, and we have to detect this problem in advance and try to put the different management units to keep the management unit working alone when the network is disconnected. Also, we have to prioritize between existing control system, because this system is going to include new intelligence in the system, but sometimes buildings has enough intelligence level, so we need to prioritize different systems. Also, we have to address different market roles and rules in different countries, so we are a wide consortium in different countries in order to have the different point of views or regulations, national regulation or local regulation regarding these future markets. And of course, this is the cornerstone of all these projects regarding smart grids, is the interoperability, in which we propose the middleware as one of the main solutions. But in any case, the interoperability is always the challenge when we are deploying and developing a new communication and coordination platform. We have several use cases. As I mentioned before, we have the smart grid in the University of Calabria, in which we are going to test the energy flexibility, test smart grid automation in real primary and secondary substations. We have the Smart Campus at the University of Malaga in Spain, in which we are going to test a district DC network solution based on PV canopies, vehicle to grid, external batteries, and specific power converter based on silicon carbide. And also we are going to install different smart batteries, three-phase smart batteries in different buildings in order to increase this flexibility expected for the project and empower this flexibility in order to interact in the power system. Also, we have other use case in Denmark. This use case is based on the residential side, but using dynamic prices in order to optimize the CO2 emissions, using as storage swimming pools. So we are obtaining a virtual storage of electricity. The idea is also to optimize the building loads using and supporting the system with voltage regulations, and also improving the resilience of local distribution network in order to support when we say resilience, we mean more in reliability, trying to avoid the congestion, to support voltage regulations, and other mechanisms related to demand response markets between the DSO and the end customers. Other use cases and demo sites, we have the district academic buildings in France, in which we are going to test interoperability issues with different energy management systems and different equipment, storage, PV system, HVAC, in which we are going to test and stress our middleware in order to know which is the final limits of our technology. Also, to test potential scenarios that can be critical, that we say resilience services. We have a lab demo in Germany in which is composed of different cubes that represent the different domains of the grid. So it is very easy to emulate different configurations and topologies of the grid in order to test the algorithms and their critical events. So our expected result, in summary, this is a project that is starting. Sorry, but I cannot show you more information, but our expected results are the modular and scalable energy management platform. Try to get a grid flexibility, a real grid flexibility with our solutions. Trying to test resilience and distribution grid solutions. The communication platform, a reliable communication platform, and also we are going to investigate about new business model, how to change the rules of the market in order that this kind of solutions can be successful in the future. So please follow us in our different online communications channel. Thank you for your attention. And if you want to more information and contact with us, you can see here our contact details. So thank you very much.
Thank you, Jacobo. Very interesting. There are no questions from the audience yet, and I will save my questions for the end. So next up, we shall shift over to the eDREAM project, and we have two speakers today. First, we have Giuseppe Mastandrea from Energy at Work, and Tudor Chiara, they will pronounce their names correctly, excuse me, from Technical University of Cluj-Napoca, presenting the eDREAM project. So, gentlemen, welcome. Take it away.
Good afternoon to everyone. I'm Giuseppe Mastandrea, and I will briefly present our project and its result. After my presentation, as said by Zia, considering that the project is really close to the end, we have decided to present a demo of one of the services developed in our project. Professor Tudor Chiara of Technical University of Cluj-Napoca will present the demo. eDREAM project is a project funded in LCE program of European Commission, and the duration of our project is 36 months. The end of the project is expected at the end of the year, but probably due to the spread of COVID-19 in Europe, the Commission will grant us 6 months of extensions. The contribution of the European community is around of 4 million euros. The coordinator of our project is Ingegneria Informatica Italia ICT company, and in our consortium are present different partners from Italy, Greece, Romania, Spain, and UK. In particular, as a CT players solution provider, engineering Atos and Energy at Work, as energy stakeholders, ASM, a local DSO interni in Italy, Kiwi Power, an energy aggregator of UK, Emotion is Italian aggregators, and Serverlect is a Romanian Esco. And also partner for the Academy, Technical University of Cluj-Napoca, CERT, that is a Greek center of research, and Teesside University. We have 3 pilots for the validation. In particular, we are in the validation phase of our project, and in particular, we are implementing a lab-based validation of the technologies and tools developed in our project in Thessaloniki, in the demo lab of CERT. And we are validating a solution for secure microgrid environment for participation in blockchain-driven demand response programs in Terni, in ASM, that is already said DSO of Terni. And we are exploiting the network of customers of English aggregator Kiwi Power for the integration of smart customers, their asset management, and the demand response network planning validation. The objective of our project is the deployment of solution for demand response that consider virtual power plants as well as decentralized approaches towards achieving a reduction in peak grid demand and real savings for the final customer. What we have done, we have implemented different components, different services, and in particular, we are demonstrating a closed-loop demand response framework designed to maintain the real-time balance of supply and demand in the centralized environment. In particular, the different technologies and services developed in eDREAM has been grouped in 3 macro groups: the techniques for demand response and energy flexibility assessment, for which we have developed the modeling and forecasting for electricity and virtual power plants, baseline techniques for baseline flexibility estimation, and also through the use of drone, multi-building demand response characterization through thermal, optical, linear information fusion for demand response aerial survey. We have developed next generation demand response services for aggregators and customers. In particular, we have developed decision-making tool, PV, RES, degradation and trend analysis, tools for big data clusterings for load profiling and customer segmentation, and visualization platform based on graph analytics. We have also developed some services based on blockchain for the control and optimization of a decentralized network and demand response verification that we will present in the second part of our presentation through a demo. In this slide is reported the idea behind our project. In particular, this idea is well represented. That is the development of a closed loop demand response environment that incorporates novel near real-time demand response verification assessment mechanism and services, and is able to involve all the interest actors, from the prosumers to the involvement in energy marketplace by means of blockchain-based technologies, and also for the evaluation of their PV plant and the estimation of flexibility, and for the pre-assessment in order to participate in the service provided by the aggregator. We have developed also for the aggregator instrument for district management, for modeling and forecasting district, and to provide to DSO the energy flexibility provided by the prosumers to solve the problem related to congestion point. Also, instrument for DSO has been developed, such as big data clustering, interactive visualization, and decision-making toolset. At this point, in this slide is present the status of the project. As already mentioned, we are very close to the end of the project. In particular, we have defined all the requirements of the project through a specific project process of involvement and engagement of stakeholders in the first phase through organization of several workshop, webinar and conference in which we have submitted to the stakeholders different questionnaires. On the basis of we have defined the services and the architecture. We have developed all the solution expected in our architecture. In June, in particular, we have finalized the development phase. We are now in the validation phase for the release of the framework and the final exploitation. At this point, I give the floor to my colleague, Tudor Chorara, for the demo presentation. Thank you.
Okay, so my demo, it will be based on a video. So since I cannot have a direct control of the video, I would prefer to have some explanation before of what you are about to see, and then I will talk over the video. So the main idea of this demo is to show how blockchain and smart contracts can be used, can be successfully used for decentralized control of flexibility and basically leveraging on smart contracts and proof of authority as a means of assuring consensus. In this sense, we have developed smart contracts that are able to connect to the smart metering device, are able to register the information gathered from the smart metering in terms of energy consumption. They are aggregated and registered on the chain. And based on this information, the other energy players like aggregators or even the SO is able to assess, track in real time the amount of flexibility that they are needed in order to assure to manage successfully the grid and to assure good balance. In this sense, the main advantage brought by this technology is the fact that the control is decentralized via smart contracts. All the players in this demo will have the role as a peer, so they are able to track and assess and validate the financial settlement of the service on one hand, and also the settlement of energy imbalances potential energy imbalances in the grid. Now I will ask some of the organizer to start
Which one, Tudor?
the video.
Which video?
The one with blockchain in its name.
Okay, here we go. All right, it's playing, but you're muted. Just unmute yourself, yeah.
So first is the role of a system operator. He can check the amount of energy consumption and production registered in the blockchain. He can check the forecasted values for that for production and consumption. Based on this forecasted value, he can construct flexibility requests. The flexibility requests are registered on the blockchain and automatically injected in the smart contracts that will manage the behavior of the aggregators in that microgrid. In case of aggregator, the aggregator is able to evaluate the potential of each prosumer that it's in its portfolio. So it can check the flexibility potential as above and below the baseline. He can check the baseline of the prosumer. And then, based on the flexibility request that he had received from the operator, he is able to construct the flexibility delivery based on the portfolio and the amount of flexibility that could be aggregated from its prosumers. Using the smart contracts and the blockchain, this is automatically injected in the smart contracts of the prosumers that are regulating the behavioral prosumers. And in near real-time fashion, it is able to assess the amount of flexibility that is delivered by each individual prosumers and also the deviations from the expected amount. In terms of prosumer, so the prosumer can have multiple options. In this case, he can see its baseline and estimated flexibility potential. He can see the flexibility request injected by the aggregator in his contract. And during delivery, the monitored energy data are registered on the blockchain. And based on that information, the assessment of the deviation compared to the requirement flexibility is done in near real time, and also in near real time the settlement of energy imbalancement and also the settlement of the financial settlement of the service is being done. Okay, so this was my fast forward demo presentation.
You want to play the other one, or you're finished?
No, it's okay. So I think the main idea are presented.
So there's no questions from the audience. I'm just curious, is that going to be open source, or is that a commercial platform that the prototype that you're demoing?
It will be open source, and the demo that you have seen, it's based on the Terni pilot. So in the Terni pilot, we are testing these functionalities of having blockchain as a technology for decentralized control. Of course, there are challenges because blockchain is well known that is not that good in terms of scalability and privacy of the data, but we have managed to overcome these problems. We have developed some second tier solution, they are called, based on blockchain, that achieve very good scalability, and also for the privacy of energy data, we have successfully integrated zero knowledge proofs, allowing the validation of the service to be done without disclosing the energy consumption data of the prosumer.
Very cool. Thank you. There's one quick question from the audience also. How is the grid security and stability ensured in blockchain, via blockchain?
Basically, it is the stability and security. It's ensured via calculating and injecting in so each asset of the grid is controlled via smart contract that is deployed on the blockchain. The role of the smart contract is to assess and track in real time the energy consumption or production of that asset. But also it has another great facility is the fact that via Oracle integration, we can inject what we are calling Gauss signal or Gauss curves that allow to adapt the energy demand of that specific asset in order to meet specific targets. For example, in this pilot case, we had adapted the demand of a building via interacting with the building management system. We have used electrical vehicles as a source of flexibility, allowing to charge or discharge these vehicles on demand.
Wonderful. Thank you very much. Excellent presentation. Very interesting. All right. Up next, is that a question? He said thank you from the question asker. All right, wonderful. So next up, we have Emmanuel Onilon from CSEM, which is the Swiss Center for Electronics and Microtechnology, and he will be presenting the TABEDE project.
Thanks, Zia. So, the TABEDE project, let me put my presentation in full screen. So, first I will give a quick overview of what TABEDE is about, why TABEDE, what is the context around, a brief overview of a proposed technical solution, and what are our test plans, and what would be our next steps. So TABEDE, it's a 3.5-year project funded by the EU, and the main goal of TABEDE is to allow a building equipped with building management system or energy management system, or without building management system, to be able to integrate energy grid demand response schemes. So to be able to make buildings demand response ready. So that's the ultimate goal of TABEDE. The Dream Consortium is composed of Tractebel in Brussels, coordinating the project. R2M in charge of dissemination, exploitation, defining the next steps after the end of the TABEDE project. Cardiff, who leads the validation, Cardiff University leading the validation and honor of one test site. Schneider Electric France in Grenoble and Italy in Bergamo, owners of test sites. CEA working on algorithms and analytics on building management schemes, and CSCM mostly working on hardware. So why do we need TABEDE? So things we have already seen in sustainable places several times in the beginning this week, that renewable energy are taking a larger and larger role in the energy balance, as you can see on the top graph, or even here in Germany, where we see between 2012 and 2020 that the role of renewable energy mostly has doubled. And not only it's good to have renewable energy, but there is a big impact in the society in terms of new jobs, in terms of economic growth, and so on. And of course, in terms of ecology with greenhouse gas emissions. But with all this power, we need to find a good equilibrium between generation, load, and storage. And this is why we need TABEDE. We have plenty of buildings that cannot enter demand response schemes, that cannot take advantages of their flexibilities, and that's why we would like to achieve thanks to TABEDE. So the main goal is that consumer can support the grid by valorizing their flexibility and local assets. So we can see that in the near future, there will be more and more flexibility, more and more deployed small-scale batteries, or even also batteries in electric vehicles. And TABEDE would like to allow the consumers to take advantage of that. What is our proposed technical solution? So we are developing what we call a TABEDE extender, so to extend existing building management system. And for that, the extender has 4 main objectives. So at the end of the project, we target TRL 7. So we won't have a product, but it will be really validated on our 3 main test sites. So one keyword in TABEDE is interoperability. So we discussed a lot yesterday morning about interoperability. So the idea is that TABEDE can discuss with several demand response communication protocols. It can be easily deployed, and it can easily be deployed in the cloud and can easily discuss with several appliances. Thanks to that, we shall be able to improve demand response capabilities. So we would like to be able to send set points to existing appliances. We want to create a database of appliances so that when someone deploys a new appliance, we can fetch the driver for that appliance, and so that that appliance can take part of the demand response scheme. And we have all the communication protocols stored in that database. And we are currently validating TABEDE on 3 test sites, and it's already working well on 2 out of 3. So our solution is a small black box, the TABEDE extender, but the solution can also be deployed in the cloud. So in the center, we have our black box or the black box virtual in the cloud, communicating with existing BMS extender. It runs a default backup solution, model-based control for local appliances. We have two main algorithms running remotely. So all the communications are done via MQTT. So one forecast algorithm, RIF, standing for real-time energy and environmental forecasting and simulation, allowing to forecast the flexibility of the building and allowing to forecast weather. So it's used also to forecast the local production. And then we have an agent-based optimization, the ABO, developed by CEA. And the ABO is the main algorithm to decide what to do with the building flexibility, accounting for demand response orders coming from the grid. And then, of course, the BMS extender has a dedicated end user interface, and it's connected to a cloud-based database that I was describing briefly before. So a quick status of what's inside that box. So inside we have a small computer based on a Raspberry Pi. We have per default already 5 communication protocols implemented in the BMS extender. And we have 3 external USB ports to be able, via dongles, to be able to discuss ZigBee, Z-Wave, and so on. And then we have some standard LEDs, status LEDs, some buttons to reset, to pair with interfaces, and so on. I won't go into details on how we communicate with devices. So the main thing are best for each device we have necessary. So if we have a device we want to be implemented in the scheme, we have to implement it's what we call a thing adapter. And the thing adapter contains a device driver, a telemetry layer, and a layer to be able to discuss via MQTT. All the communication in TABEDE are based on MQTT. We have a dedicated end user interface, so showing what's going on. So for each appliance, we have a widget. So the end user can add a new appliance so that we can fetch the necessary drivers, and we can see all that's going on in the building. We can see the forecast and so on. We can see what the ABO algorithms, the algorithm would like to do with the appliances. So if one day the TABEDE solution is commercialized, that's what it should look like in a living room. Concerning the test sites, we have 3 main test sites. One in Grenoble in France, so Schneider Electric France. So it's a commercial building, quite challenging, but we are getting there. One test site in Bergamo, Italy, residential building, and a smart house related to Cardiff University, but it's a residential building. So Schneider Electric building is a large building, and we would like to see how the TABEDE solution will behave with implicit and explicit demand response schemes, and we would like to show the advantages of its TABEDE solution for such a large building. And we have to say it's quite challenging because this building is already very, very energy efficient. Second test site, Bergamo, Italy. So residential building, we have different use cases. So the first one is, it's a law in Italy. So we have to respect a maximum 3 kilowatt power request from electricity provider. Then we want to we want to adjust the building consumption, and then we want to decide what to do with the excess solar PV generation. In this building, there's a large water tank in which we can store energy. Last test site, the Cardiff building, in which we have also 4 different use cases. So here, of course, we want to see how the building will behave with respect to demand response orders, but we want also to validate the model-based predictive control solution. So R2M has done an awesome job disseminating TABEDE. We are very active on social media, as you can see here. You can download newsletters, and we have several go-to webinars. And we would like to welcome you to the next webinar. So you have just to click on that link, and you'll be there. And that's about it for TABEDE.
Thank you, Manu.
You're
I
more
can't
than
ask any.
welcome.
I can't ask any questions because it would be a plant since I'm in the project.
Yeah.
And there are
But
none
we
from
can
the.
only advise you to follow the next webinar.
Yeah, the slides will go up with the video, and there's also a post-workshop survey for everybody. So thanks, Manu. I will ask some questions to everyone at the end, but for now, let's shift over to Alexander Kavskik. I'm sorry if I mispronounced your name, sir, from Typhoon Hill, and he will be presenting the DRIVE project. Take it away, Alex.
Thank you, Zia. I hope you can see me, and I hope you can see my screen
Yes, you're all set.
this time without the presentation mode. Okay, so thank you, and I'm really honored to be presenting the DRIVE project. I come from Typhoon Hill, but this is a big project, and we would like to show you how DRIVE unlocks and unlocked before that demand response potential, and how we use digital twins for that. So in the presentation, I will tell you what and who participates in DRIVE, what we are doing, how we do it, and why we ended up using digital twins for that, and what general benefits of digital twins we see right now and in the future, especially in this domain of demand response. So this presentation is very generally and loosely based on the article DRIVE Unlocks DR Potential and De-risk Implementation, which was published in the European Energy Innovation magazine. So because time is limited, and I already used a minute, what is and who is DRIVE? So the DRIVE is a demand response integration technologies project. That's what the acronym stands for. And we have the aim of unlocking the demand response potential in the distribution grid. You can find more info, deliverables that are public, etc., at our project, which is linked here. And if you have to describe it very briefly, it's about developing cloud gateway infrastructure where we can aggregate both residential and tertiary buildings for demand response control, but also provide ancillary services which are extremely lucrative. You can earn a lot of money in the flexibility market, and these services such as frequency FCR, Frequency Containment Reserve. So it's sponsored by EU. The EU contribution is just shy of 4 million. And we are ending in November. So we are in the final stretch. We are doing final validation activities, result assessment, wider uptake. and we are thinking about how to make this more commercial, how to use it for additional innovation. And we have 10 partners. I will go very briefly. Airbus is in charge of cybersecurity, so this is not the aircraft division. We have gateways as the cornerstone of our DR capabilities, so Airbus is in charge of making them hack-proof, or let's say at least so difficult to hack that hackers will give up. CA is in charge of multi-agent systems, Cardiff MPC model predictive control, COMSA, Blonog, Wendt, and Scholt are owners or operators of several pilot sites. And Ervalis is the aggregator who communicates with DSOs and BRPs such as Scholt. ILECO is in charge of layered energy community algorithms, and originally the concept of blockchain energy coin. Typhoon Hill, where I come from, is in charge of validation and creation of digital twins and the validation platform, and R2M is in charge of coordination, dissemination, wider uptake, etc. So what are we doing? Our goals are twofold. From the point of view of prosumer and consumer, we want to actually make 20% of load in residential and tertiary buildings available for DR. And that results in cost saving for price-based DR and maximize revenue for prosumers through incentive-based DR. When it comes to the other aspect of the project, we actually aim at DSOs, BRPs, and TSOs, where we want to increase their capability of renewable hosting capacity up to 30% reduction of capex and opex, for example, by just controlling what you already have, but you haven't controlled. You don't need to do grid reinforcement. You just take care of congestion by changing the operational parameters of your flexibility assets. So what specifically are we then doing? I will skip details because it's a huge project and we did a lot and we succeeded in virtually everything that we set out to do. So most important use cases for consumers and prosumers are time of use optimization and kilowatt max. When it comes to BRPs, it's portfolio management. The platform allows BRPs to reconfigure their assets in the portfolio. From the point of view of DSO, it's mostly about congestion management, but we also prove that we can do voltage and power quality support and, for example, reactive power control, which are very important for reduction of capex and opex because you don't have to fix the issues in the grid by investment in physical assets in the grid reinforcement. You can do it through smart control, and of course for TSO, FCR, FRR, and we are doing it at 5 pilot sites physically, mostly in the Netherlands. We have a Devo district with residential buildings and a centrally controlled heat network where we can actually optimize and control the heat network. In the Woerden district, we have 39 houses that have PV panels, batteries, district battery, controllable heat pipes, Aido Stadium with PV panels, a large battery, EV charging poles, which do not support vehicle to grid, but there is a capability to do changes in let's say in charging rate of the electric vehicles connected to them. The Giesenwind site is a large wind turbine site with 3 wind turbines and a large 1 megawatt battery. And in Spain, we have a COMSA headquarter building which has solar panels, is installing a battery, and has a very advanced building management system with many HVAC units that we can control. So if you look at it, this is a very nice portfolio of traditional residential assets for DR, smart residential assets like the Woerden district where you have PV, house batteries, controllable inverters, etc. And of course, tertiary buildings like Aido Stadium, Giesenwind, and finally, office buildings like COMSA in Spain. And how we do it, it's a cloud gateway infrastructure. The cornerstone from the point of view of the prosumer or consumer is the gateway. The gateway communicates fundamentally with this smart power suite developed by Enervalis, and this is the heart of the aggregation. And the aggregator is capable through meta language and translation between different DSO, TSO requests to actually trade with flexibility, both in day-ahead market, also to reserve flexibility, etc. And these are our DSO and TSO partners, Tenet, Stedin, Leander, and BRP Schultz. So the biggest issue and the main topic, so I will not go into details, this works. This is in a very high TRL commercial stage. These sites are actually, especially Giesenwind and Aido, they are already physically running DR programs. I want to focus on why digital twins were important. So in the project, we created 4 digital twins. So the sites with the digital twin are the Woerden, the Aido Stadium, the Giesenwind, and the COMSA headquarters building. So let me just explain then why this was important. So I mentioned the Woerden site has 39 smart houses. They look like this. They have PV panels, each house 3 kilowatts. The inverters are controllable, but initially we were not allowed to control them. There are 5 kilowatt controllable heat pumps, and some houses have alpha and 5 kilowatt batteries, and there was also installed a big district battery, 500 kilowatts. When you need to implement DR, one of the biggest problems with implementation is that you claim that you can do everything, and you are supposed to then, simply start testing it. But there is a big reluctance by building owners, site operators, everybody, whether this physical testing will work as planned. So if you look at physical testing like this, we have our drive with all the DR capabilities, additional services, and you then have to control physical devices through your gateway. These are usually Modbus controls, and of course you have human beings interacting with these devices and setting the reference values for indoor temperature, etc. When you do physical testing, there is a possibility that your actors may get angry because there's no hot water and they want to take a shower. But that's not the biggest issue. They will forgive you after some time or forget. There's also a possibility that due to maybe, unplanned behavior of your control algorithms, you can fry the inverter. The inverter can catch fire and then, you can damage stuff. The digital twins proved crucial, at least in some pilot sites, to de-risk and provide confidence to site owners that everything is going to work. So when we say digital twins, some people would call it hardware in the loop or hybrid cyber-physical testing. So we have the same infrastructure, the drive logic is the same, execution platform is the same, gateways are the same, but instead of real pilot sites, you are controlling the validated models, digital twins of all the assets that you can control in the pilot sites. And you have historical real-time data to feed your emulation. This is not simulation, this happens in real time. The biggest obstacle there was actually to validate these models. So we set up this, let's say, approach. So if we have physical before, virtual before, physical after, and virtual after, we don't have time, but fundamentally you validate that your digital twin can communicate like the real asset, and then after that you make sure that it behaves like the real asset. And when the statistical differences are negligible, you have a validated digital twin. So for the Woerden model, this is what the model looks like, but on the surface. Each house is one block, but when you click on each house, this was done in Typhoon software, but runs in Enervalis premises. you actually have additional signal processing and the models of inverters, models of heat pipes, etc., together with control logic. And this is what it looks like at Enervalis premises. So we have real-time emulators with ABB gateways that you use at real pilot sites. So the top layer are emulators, the lower layer are gateways. So the drive in the sandbox mode thinks it's controlling the real assets, but it's controlling actually the models. So this setup allows us to run parallel models, to do to try portfolio management changes, to do benchmarking, etc. And in the case of, and then we can visualize everything in Grafana. We can see test results in Allure. We set up everything so that it's remotely available to all partners through GitLab Pipe Runner. You just say, I need a COMSA model for 2 days, run it, and you run your MPC or mass optimization there. And for example, for Woerden, this is how we did congestion management, frequency control, voltage control, power quality, so with 39 houses, so that there was a confidence that we should be allowed to control inverters, for example, which was not originally planned. The similar thing happened with the COMSA building, where the building manager wanted to see in the digital twin that our control messages will not mess up the building management system, and we managed to prove to the building manager. So here are just some screenshots. Unfortunately, we don't have time. As I mentioned, this is a huge project, and we did it at many sites, and it's both physical, and before that it was digital and virtual. So here you see a Giesenwind, for example, test result. Here you see early stages of the COMSA model being validated, where there were discrepancies that were then eliminated and the model was validated. So generally, we see digital twins as a very important tool in making DR happen. You can use the digital twin to test your algorithms extensively and be confident that they work. But then you can actually show it to the pilot site owner or the customer that it will work, so they can have full confidence. It also allows very simple, let's call it troubleshooting. There are different Modbus registers at different sites, different assets. When you try to make it happen with traditional gateways, it takes sometimes days to make sure everything happens. Here, you have a digital twin, you set up your registers there, make sure they work, and then you just push the Modbus map to the gateway, and it works. This is exactly what we did at several pilot sites for several devices. You can do pre-certification for different grid codes using digital assets without the need to do any physical testing. You can do benchmarking and, you know, different very long tests. And in the future, we see this as a very important tool to explore new business opportunities, to show new financial models for business, to actually prove to DSOs, BRPs, and TSOs that these solutions are good. And in the long run, for example, for cybersecurity, you can use digital twins to generate clean data, and then artificial intelligence can use the clean data in the production side to easily recognize hacking attacks of the gateways. And generally, you can use these digital twins to streamline system integration and help your system integrators. So thank you for your time. These are our social and web links. Visit our website, follow us on Twitter and LinkedIn. We are hopeful that very soon we will have also our public reports to show you more details. This is just the tip of the iceberg.
Thank you, Alexander. Very innovative to use the digital twins to de-risk. I like that approach. We do have one question from the audience. Is any of the software open source? And if so, which part?
Well, the Enervalis itself is a proprietary system. When it comes to Airbus cybersecurity layer, many of the components that they are using are open source, but I'm not an expert there. On the website, you can see that in the deliverables, you will see mentions of the cybersecurity tools that Airbus was using there, and most of them are open source. It's the integration which is, let's say, done by Airbus. And there, it's very important also to have the bandwidth, because gateways need to report to the central threat detection. They have to report some things. So, for example, 5G will be crucial to provide even better protection. And when it comes to digital twins, actually Typhoon Hill software, where we created these digital twins, is not open source, but it's free. So you can download it from the website, and the models, because they are funded by European Union, they are actually free. And there are some models included as examples in Typhoon software. The only issue there is that without the hardware emulators, you cannot run these digital twins in real time. So you will have some, it's more like simulation. It's not emulation, but fundamentally the digital twins are actually accessible, not open source, but you can export from our software into NCC, for example. So you can use it in MATLAB, let's say.
All right, thank you. And I just have one quick question. I saw on the slide part 2, where are we doing this physically? You had Stedin and Leander DSOs and Tenet TSO and Smart Power Suite. Does this mean that you've consulted with them or adopted their technologies, or what is this rationale here?
Well, since these are physical sites and we had to do physical testing, we actually cooperated with them. Schott is even a partner in the project in the role of the BRP fundamentally. So Stedin, Leander, and Tenet, they actually are supporting the project. And the Smart Power Suite has capability to interpret different commands and requests and flexibility requests from different DSOs, BRPs, and TSOs, but right now these capabilities are 100% implemented exactly for these DSOs. But Enervalis has a kind of meta language for these DSO, BRP, TSO commands. So depending on legislation in Spain, you cannot, for example, do what you can do in the Netherlands. So that's why in Spain we didn't do really physical testing. So they will be able to provide these same capabilities to other DSOs in other countries and parts of the EU. I hope I answered this.
Yeah, definitely. No, it's interesting. It's good that you're consulting with them. I did notice that so far out of the 4 projects, only ebalanceplus has a DSO in the consortium. So I will be bringing this up at the end when we all have a round table if there's time. But as we all know, DSOs are critical to demand response adoption. So thank you very much, Alexander. At this point, we shall move on to HOLISDER project, and presenting that will be Arun Subramanian from TNO. The floor is yours, sir.
Hi, I hope you can see my screen now.
We can, thank you.
Yeah, there you go. Yeah, it is visible. Hi, everybody. Thanks for joining in. I'm Arun Subramanian from representing the HOLISDER project, working at TNO in the Netherlands. TNO is one of the knowledge partners within the HOLISDER project. A little contrasting to the presentations you've seen so far, I would focus less on the entire project itself. HOLISDER is a huge multi-million euro European project, and I would rather focus on one aspect of it, which involves using flexibility, demand response, and the distribution network. So my presentation is called Active Voltage Control in a Distribution Network, which we demonstrate using a co-simulation framework. So if I can move forward, the presentation itself is divided into 5 sections, giving some information on the background, where we fit in within HOLISDER, what the motivation is, and what are we trying to co-simulate, what are the phases within the co-simulation, what is the use case that we've taken from which we've extracted data, we've extracted information to perform our co-simulation, and finally what our conclusions are. Among the objectives of HOLISDER, now this is something I've picked out from the HOLISDER website. There is let's say a call for introducing residential and tertiary energy consumers as active players within the energy market, and coupling that with one of the objectives, which is for safeguarding grid reliability by means of complementary demand response strategies, which also combine using flexibility that is available within the distribution grid. And also there is a call for validating these solutions in real-time environments, ensuring consumer engagement in DR. My focus, or our focus within the part of the project that I'm going to present right now, is developing system impact simulation tools which actually combine these three aspects of the project and then demonstrate the viability or the feasibility of such a co-simulation or an algorithm in a co-simulation environment. Our motivation, yes, I think this is something that is more known to everybody who are working in this domain. We are moving towards a carbon-free system, both in the transmission side of the electricity network and the distribution side. Within the distribution side, one of the things we see are the adoption of a lot of technologies like PV panels, micro CHPs, batteries, etc., by residential and commercial users. What happens as a result of this is distribution system operators expect to see increases in operational issues such as power quality management, like over and under voltage issues, congestion management, handling overloading of assets, etc. One of possible solutions to mitigate this problem is automated demand response, and then that being done to flexibility sources within the distribution network. Among all the flexibility sources within a distribution network, this particular use case that I'm going to demonstrate focuses on commercial buildings as a potential source for flexibility in the distribution network. Why commercial buildings? Well, they account for around 11% of the total energy consumption in the UK and EU, and 18% in US. This is according to statistics from 2003. You can easily assume that within the years that has passed since this data collection, the energy consumption has only increased. HVAC accounts for, HVAC stands for heating, ventilation, and cooling, accounts for 50% of this energy usage within the building itself. It also presents us with a possibility for extracting flexibility, where smart control strategies of smartly controlling this HVAC systems could, without affecting the comfort of the building occupants, could actually give us some flexibility to play with in a local energy market involving the distribution grid. So, presenting the problem itself, when we look at trying to solve a problem in the distribution grid, we first wanted to know who the stakeholders were, who were the people responsible for providing services and for getting incentivized. We have many different customers who are affiliated to an aggregator. An aggregator is a person who is agnostic of grid constraints or problems within the grid, but he is aware of the flexibility portfolios of all of his customers. Armed with this information, he can provide flexibility services to another stakeholder, the DSO, the distribution system operator, who is aware of grid constraints but unaware of flexibility of the different customers. The DSO himself also is unable to know, I mean, it's also not possible for the DSO to directly actuate the various flexibility sources within the consumers. That is something that the DSO can then request the aggregator. The aggregator, with all of this flexibility information, can actually then perform actuation or request customers to perform an actuation. Given these problems, we realized, okay, there is a possibility to trade flexibility services in return for incentives. We wanted to identify what flexibility services can be provided to the DSO, And in this case, like we've heard already from different presentations, congestion management is hot topic. Everybody would love to know how congestion management can be performed within the distribution network by manipulating flexibility. In our case, we wanted to look at voltage control. Voltage control being a driving factor, mainly because of the added PV penetration and added distributed generation in the distribution network, causing voltages to increase above certain thresholds, causing more maintenance costs for the DSO. How we managed to do this, or how we want to, now that we've identified the problems and the stakeholders, we wanted to come up with a flow of information and sort of a communication diagram between the aggregators, DSOs, and various stakeholders involved. How the players within this sort of a co-simulation environment, the customers many are multiple flexible commercial buildings, the external grid itself or an abstraction of it, distributed generation such as a PV park, which is again connected to the distribution network itself. All of these stakeholders form what we call the distribution network itself. So they provide their flexibility to the aggregator itself, and they get this information for their flexibility by means of a thermal load simulation. So since we said we're focusing on the HVAC part of the commercial buildings, we needed a simulation tool or model that can calculate for us what happens when the heating HVAC system changes in actuation, what are the differences in electricity consumption as a result of changes in HVAC schedules. So we rely on a thermal load simulation to provide us that information. The flexible buildings would take that information and convert that into a sort of flexibility that the aggregator can understand. The aggregator, having aggregated all of this flexibility, then talks to the DSO by means of a grid simulation. A grid simulation gives the DSO an insight into the state of the physical grid itself, the physical distribution grid itself, and the aggregator can aggregator in this case is responsible for balancing the network as well, so determining how much of energy is to be imported from the external grid, how much of it can be used from local production, and it determines a sort of demand supply solution which balances the distribution network. This solution leads to consumption or production of many different flexible assets within the distribution grid, and this actuation is actually fed into a grid simulation so that the DSO can observe what happens to the state of the network if this demand supply solution was actually provided or actuated. The aggregator then and the DSO then takes part in a sort of iterative communication with each other, where the DSO observes the grid simulation and identifies if there are voltage problems in any part of the network and informs the aggregator, hey, there is a problem on this part of the network, do something about it. The aggregator with information about flexibility in that particular node can actually tweak or change the actuation at that particular node, perform a new balancing, and then feed this information again to the grid simulation. So this loop continues until the DSO is satisfied with the state of the network, saying, hey, there are no more voltage issues that I need to worry about, or they've exhausted a certain number of iterations within which the problem could not be solved. So we would like to observe this as well, because since we are running a simulation environment, we'd like to see how many times were voltage problems not solved. So this gives us an insight into the algorithm that we are following and helps us tweak the algorithm and make it better for the future. Once the aggregator arrives at a solution that the DSO is also happy with, the aggregator can then communicate this information back to the participating nodes within the distribution network by communicating a price signal. Now, flexibility and price, these are terms proprietary to the algorithm that we are using within the aggregator uses for demand supply matching. And this price signal informs all of the buildings, all of the nodes, how much they have to produce or consume at that given time step. Now this whole step repeats again for the next time step, which is maybe an hour or 15 minutes, depends on how often flexibility needs to be aggregated within this simulation. A small introduction to the technologies we are using within this simulation. As I said, there were 3 simulation modules that we depended on. SM is an open sourced simulation tool and collection of models which was developed by TNO and open sourced recently. It is a discrete time simulation tool. What it does is it calculates energy flows and performs balancing of multi-commodity networks. In this particular instance, we are using this feature of SM to simulate for us and the work of an aggregator. Another advantage of using SM is it can interface easily with other simulation tools and models, and this is something that we use for plugging in the EnergyPlus models. EnergyPlus is a simulation model that simulates thermal zones and solves HVAC system responses, also taking into account radiant and convective effects of interaction between thermal zones and the environment, and gives you calculations such as energy consumption of a particular building at any given point of time, given a certain set of parameters such as glazing, insulation, what are the sort of heating and cooling set points that you've set, what sort of ventilation is applied, what are the devices that are used for heating, such as a heat pump or district heating, so on and so forth. Another place where SM, the aggregator, interfaces with is OpenDSS. OpenDSS for us provides the grid simulation. So given the demand supply solution at any given point by the aggregator, this information can be fed to to a network that is modeled in OpenDSS, and OpenDSS for you can calculate the power flow in the electrical distribution network, and then this is the state of the network that is observed by the DSO itself. A quick look into the architecture now, that since we had a sort of an ambitious reach for trying to simulate multiple devices together, we wanted an architecture which was robust enough to handle many different changes in the simulation. We should be able to simulate multiple scenarios. We should be able to visualize the network itself and the results of it, and also make sure that all of the simulations which are running in multiple different processes can be deployed across different virtual machines or PCs, and they can still communicate with each other as though they were all running under the same within the same memory. So on the top, you would see the user interface, which consists of a tool called the Esdl Map Editor, which is again open source, which allows us to draw the distribution network itself, and which allows us to draw the distribution network itself and configure it with parameters that are needed for both the aggregator and the DSO. Within the aggregator simulation itself, we connected assets such as the HVAC system in the buildings to an asset model that was modeled in EnergyPlus and interfaced with Python through a message bus. The aggregator itself talked via another message bus to OpenDSS, which is the physical grid simulation, and the DSO could observe the same and then communicate its findings back to the aggregator, saying, okay, there are issues within the network or not. All of the data that is simulated is stored in a database and visualized so that the user can take a look at the simulation results that just happened for the scenario that he wanted to simulate. So, going to the three phases of the two phases of the simulation itself. The first part, where you saw that flexibility was sent from all of the actors, the agents within the distribution network to the aggregator. we use an instrument known as a bit curve or a demand function, which is actually a function of power or energy over price. This gives an insight into how willing each of the actors are to deviate from its original requirement of energy. And this gives this is the language that the aggregator talks, such that it can perform balancing of the network itself. And after having determined a solution, it talks to the DSO about the possibilities of using said solution. Now, in the second part of the aggregator's working, it sends down a price signal. The price signal is something that each of the actors can use with along with its bit curve to determine how much it has to consume or produce at a given point of time. Now, this in a normal situation, this seems fine. The given price are sufficient for all of the actors to act on the flexibility that they have promised to the aggregator. However, things get a little complicated the moment some issues occur, such as on a very sunny day when there is overproduction of energy from the solar. At the PV park, we see that there are over voltages on 2 nodes of the network and none and normal operation on the other nodes. In such a situation, the aggregator, after consulting with the DSOs during the loop that you saw earlier, could incentivize these actors to consume more than what they originally wanted. By doing so, by consuming more, they can the relationship that you see with power and voltage in a network is that by incentivizing consumption, you can actually bring the voltage down. The same thing happens with under voltage as well. So in situations when there is under voltage, the aggregator can incentivize production or de-incentivize consumption to try and solve under voltage problems in the distribution network. Now, within the scope of the HOLISDER project itself, we took there are a total of 4 pilot sites within HOLISDER across the globe. One of the sites was in Finland and involved a commercial building. And what we did was talking to the partners who were involved in this particular pilot, we could get some measured information. This was from sensors within the building itself and some known information about the building itself. We took that into account along with the assumption that this building, which was now being heated by district heating, would convert to an electricity-based heating, such as a ground source heat pump. Now, the reason why we assumed this was so that we could manipulate the flexibility provided by the thermal mass of the building in the electricity market. So it was possible for us to assume that an electrification happened. With these information, we could build a digital twin of this pilot building, which was identical to which showed an identical nature to the consumption pattern of the finished pilot building, but with the assumption that it would provide this heat by means of a heat pump. Now, in addition to this information, we also needed to come up with certain scenarios for driving the HVAC system. So there was a base case, which was from literature. We found out certain set points in heating and cooling and ventilation rate, and then came up with the consumption, which was similar to which was in the digital twin of the finished pilot building itself. The problem and what we wanted to vary were these 3 certain parameters, but we also needed a KPI to confirm that by varying these parameters, we do not bring discomfort to the occupants of the building itself. So we took into account the comfort that is calculated within the model itself on a scale known as a PMV, or a predicted mean vote, which is a scale on something known as a Fanger model of comfort within the building itself. So the aim was to come up with a couple of scenarios where we changed the set points such that the comfort level remained the same, or actually in this case, it actually improved. Not only did it improve, it gave us also a lower consumption of electricity for the same building. And we came up with another scenario as well, which was within the same comfort range as the original base case, but again gave us a lower energy level. So with a total of 3 energy levels, we had three equally lightly flexible states that the building could shift to if and when requested by the DSO. Now, extending this this particular building, we also created 4 more buildings which are not identical but changed in behaviors, in parameters, such that they were different in building square footage, so that the demand varied. We also changed some of the parameters inside of it, so it represented 4 different kinds of demands within the distribution network. We also added a PV park in there with a generic PV park profile, and also some line parameters so as to make a sort of fictitious distribution network that we could simulate and then test our algorithm to see whether it was possible to trade flexibility services with DSO. A very quick demo that I can do, showing you what we have. So I hope my screen is visible to all. What you're seeing here is the user interface where we configured the network itself. This is called the Esdl Map Editor, another open source tool that was developed within DNO itself. And you can see the distribution network, the fictitious distribution network that we developed for testing our algorithm. There are buses in place, there are cables in place, and they're all parameterized based on information that is necessary to be used by the grid simulation, for example. We also have the various buildings within this network, wherein we could say each building had a battery, a demand which was associated with the HVAC system. So this is where the external model EnergyPlus would plug in. We had also inflexible demands, so static loads which would never vary. And we also put in another flexible source in there, which was a PV panel. So such was the configuration that was given to all of the devices, the buildings themselves, and we connected, and we had an abstraction of the external grid as a producer, as an infinite producer. So what we could do is we could run a simulation here as per the statistics. So I'm going to run for a week in February, which is, it is possible for us to configure this way. And we, I'm not going to specify anything, and then give run. And then once the simulation is complete, we can open a dashboard to take a look at the results. So what you're looking at right now is all of the results that are populated from the co-simulation that just happened. So it's divided into 3. We have the results from the aggregator itself, the results from the grid simulation, and some statistics which we would like to use to measure how well the algorithm worked. So in this situation, from the aggregator, what you're looking at is raw data of demand supply matching that happened in the distribution network. So every value that you see above the x-axis, above the 0 line, are consumers. Everything below the 0 line are producers. And we can see how at every time step the total demand is met by either importing from the grid, or during the day you can see how the PV park is able to contribute to the production. The aggregator also does some other calculations, which I'm not going to get into, which is really energy flows within the various transport assets in the network. What is more interesting for us is really what happens to the voltages in the network, and this is captured by OpenDSS. This is the grid flow simulation, and you can see that at some points in the simulation there are voltage problems, which where a voltage problem is in here categorized as an instance of time when the voltage goes above 1 per unit, not really volt. This is 1.1 per unit, so which is really roughly 110% of the rated voltage at a given bus or a given node. So you can see that there was an instance when the original solution actually caused a voltage problem, but it was solved by you can see the green, which was the final voltage that was measured and the accepted solution by the DSO. And in this case, something was done, some curtailment was done so as to solve this problem. Now, there are also instances, as you can see on this day, on the 22nd of February, that we saw situations that could not be solved using all the flexibility within the distribution network. This is also an acceptable problem that can exist within the distribution network. And this is one of those instances where the DSO and the aggregator tried iteratively to solve a problem, and they could not, even after they used all of they've exhausted all of the flexibility within the distribution network. If you actually take a look at, if I zoom into one of the days where there was a simulation where there was a voltage problem, I'm looking at the heat demand within the particular building. So this is building number 21, where you can see that originally it actually wanted the green curve shows the original demand that the building put forward, but the original demand actually resulted in a voltage problem. And then it was asked, oh sorry, the yellow is what it actually required. This is the desired consumption of the building, but that resulted in the voltage problem. And to bring down our Nova voltage, as I explained earlier, the aggregator incentivized consumption. So asked the building to consume more, and then the building could consume more because it had another flexible state that it could jump to, which consumed more than its current state. So it could do that, and with that jump, it could actually solve the voltage problem, because once it performed that, you can see that the voltage is no longer above the threshold that was measured. Now, as I said, each building not only had flexibility from the thermal demand, but it also had batteries inside of it. And batteries also play a big role in solving these problems. So for example, you can take a look at the states that was required to run. So the batteries could wanted to let me guess discharge at certain points. So discharge is also shown as positive here, but however it was asked not to do so owing to the problem of voltage that existed at that given time. If you look at PV panels, this is also something, another source of flexibility within the building. And you can see that, yeah, the PV panel also wanted to produce more because there is a lot of sunlight available during the day. However, it was asked to curtail as a result of the voltage problem that existed. So what we could see is all of these flexible sources coming together to solve the voltage problem that existed in the grid. And we, as I said, we wanted to also measure some of the statistics of the simulation. So one of the things we wanted to see was during the day, during the week, actually, how much how many voltage problems were actually solved during the entire duration of the week. And we see that there are some problems that were left unsolved. So there are problems in the node that were left unsolved. But for most of the cases, they could actually come to a conclusion, a proper working environment with the grid. So coming quickly back to the presentation. So some of the results that we saw was larger the thermal mass of the building, more flexibility it had, and greater its contribution was to solving the voltage problems. So since I told you, one of the ways we simulated this was by making multiple buildings, some buildings with larger thermal demands than the other. And we saw that the larger thermal demand buildings could actually contribute greater to solving voltage issues. And then another observation rather is that the voltage problems are more severe closer you are to the source of the problem. So further you are from the feeder, for example, if the feeder is actually causes the problem, then the lesser you will be affected by a voltage problem. We also did measure some of the KPIs, like the final heating control strategy. So among the 3 strategies that were predetermined, the buildings would eventually calculate what happens with the final heating, the control strategy of the hatchback. And we saw that it was with the same level of comfort as each of the predetermined scenarios. So this was within the category 3 level of acceptance of temperatures, air temperatures within the building. We saw that the final allocated heating control strategy actually resulted in savings in the energy bill for the buildings themselves. And this was around 20%. And here we have not even considered the flexibility incentive it would get from the DSO for helping solve the problem. We have a lot of work to do.
Excuse me. Sorry. Yes. Can you wrap it up, please? It's quite long.
Yeah, I'm done with this. So there is a lot of scope to improve from here on. I'm more than happy to take any questions from the audience at this point.
Thank you. Great presentation. Just really quickly, can you answer which signals between the aggregators and the DSOs are needed for balancing or peak versus grid stability management?
So the aggregator would determine a balancing solution. So there was power in terms of megawatts in each of the nodes, and this was fed to the grid simulation. The grid simulation would calculate things like per unit voltage, as you saw in the panels, and other power quality parameters which the DSO can observe. So there are a list of things that, such as it depends on also the load flow that you are calculating. It could come up with VAR calculations, phase calculations, voltage calculations, etc. So these are observed by the DSOs, and the DSOs can then have internal logics on what it thinks is a stable grid, and what information it needs to use to tell the aggregator that, hey, some part of the grid has lower power quality or is unstable and needs to do something about it.
Great. Thank you very much, Arun. Just for housekeeping's sake, we have 3 more presentations. And then for the sake of time, I'll hold all the questions until the end, at which point we can go as long as we need. But I just want to respect, if people need to leave, that they can leave by 18 o'clock. So thank you very much. We'll swiftly move over to Joe Southernwood from IERC, which is the International Energy Research Center based out of Ireland. And Joe will be presenting the Novice project.
Great, thank you very much, Zia. I'm just gonna open up the presentation so you can see the slideshow. Great. So thanks very much. So my name is Joe Southernwood, and I'm a senior research engineer and head of the Integrated Energy Services team at the International Energy Research Center. I've been the project coordinator for the Novice project, and this afternoon I'm going to talk to you about some of the learnings that we achieved during the project, and I'm going to switch direction a little bit from what you've heard earlier today and talk less about the technology and more about some of the business models that support the energy transitions as we move towards this idea of a flexible energy network. So to set the scene, you've heard this afternoon about a number of really innovative demand response and flexibility solutions that already exist or they're in development. And the same is true of energy efficiency solutions. There are lots of innovative products out there that already exist that need some assistance to be deployed into the market. And what we know is that at the moment, uptake of these solutions and market penetration is still quite low, and it's taking some time to really integrate those innovative solutions into the market. So what I want to do this afternoon is talk to you about the business model side of things, because I think it's really important to understand that the technology is one part of the problem. What we also need, in addition to the technology, is some really compelling business models that will assist building owners and building occupiers to take up these technology solutions. You heard earlier from one of the speakers, I think from the DRIVE project, about the difficulties of persuading building owners, building users, decision makers to take up these technologies and the challenges that you can face in doing that. And so I think it's really important to consider not just the technology side, but how do you engage with the users? How do you build a business model that works for all the stakeholders through the value chain, from the building users perspective through to those who implement the solutions, through to the network operators that can give some value to those solutions. So I'm going to talk about one such business model, which is the Novice model, which we tested during our project. There are many others. There are many other projects that are doing similar tests. But today we're going to talk about Novice. So Novice took the approach of integrating flexibility into energy efficiency projects. And the idea was to integrate it specifically into energy performance contracting. So on the screen now, the diagram you see, the shapes that are in blue show you the traditional contracting methodology for energy performance contracts. So typically what happens is a building owner or an Esco, so an energy services company, takes some financing, they use it to implement energy efficiency measures into the building. As a result of those measures, the building energy consumption drops and the bills reduce. And the building owner uses the savings that are generated to repay the initial financing. Now that all sounds fantastic and works great on paper. In practice, it's not a compelling enough business model to drive the uptake of EPCs around Europe. And if you look at the different countries and the various member states, the energy performance contracting markets and the state of building renovation is at various levels of maturity. But in general, building renovation rates are still very low. So what Novice is looking at is saying, well, okay, we'll do the same thing. We'll take some financing. We'll use it to implement energy efficiency measures. But what tends to happen when you implement energy efficiency measures is you also you can upgrade the smartness of your building. And it's through things like upgrading your building energy management system to give you better control of the systems within the building, or installing solar PV panels, perhaps with battery storage, perhaps other renewable energy technologies. Perhaps you're installing heat pumps or electric vehicles and electric vehicle charging points that give you an opportunity to access the building's flexibility potential that otherwise wouldn't be there without those energy efficiency projects. So what you end up with is a second revenue stream, and that's shown in the diagram here by the green shapes. So you still have your energy saving revenue, but now you also have this second revenue stream from offering demand response services to the grid. So this requires the services of a demand response aggregator, as you've been hearing about earlier this afternoon, who can offer that flexibility to the network operator and receive an additional revenue stream for it. And the idea is that that improves the business case for implementing these measures in the first place, and increases the uptake of these measures in the market. So just having a look at the traditional model, the way this is normally done is that the energy services company, or the Esco, normally would handle all the energy efficiency measures. So they have a contract with their building owner that covers a package of measures to reduce the energy consumption of the entire building. And that covers everything from finding the financing, dealing with the energy supplier, the consulting and engineering that goes behind the design, dealing with installers, technology suppliers, and then measuring and verifying the energy savings that have been achieved. If that client also wanted to participate in flexibility services, they would need to also contract with a demand response aggregator who handles offering that building's flexibility potential to the grid. And what that means is the client must manage contracts with each party. They must understand what they're getting into, and that can create conflicts in terms of baseline discrepancies or operational conflicts, sometimes even contract breaches, because the two don't necessarily work seamlessly together. So what we propose in Novice is that instead of having two separate contracts, you actually make better use of the Esco contract. The Esco already has a contract for energy efficiency with their client, and could manage the relationship with the aggregator party as just another contract, another service that they manage on behalf of their client. What this means is that from the client's perspective, it becomes more simple. They only now have one contract to manage with the Esco, who handles everything, including offering the flexibility services to the grid via the services of a demand response aggregator, and the Esco manages an additional contract, which could be a memorandum of understanding to govern the relationship between Esco and aggregator and determine how those revenues get distributed between all of the parties in the contractual arrangement. And as I've mentioned, the benefits of this are that you can have a shorter payback period. There's a consistency between the baselines that are in use by the Esco and the aggregator, which should reduce any contractual complications that might occur and ensure that there's operational consistency of the equipment that you find on site. So I'm going to look at a case study now that we used in the Novice project. This is a case study for a supermarket based in Ireland. Ireland is lucky enough to have a very, relatively speaking, mature demand response market with lots of opportunities. And in our consortium, we had an Irish-based Esco partner. So they spoke to one of their clients, which was a supermarket, and they looked at the energy efficiency opportunities that exist for that building owner. And as you can imagine, there are the typical kind of energy efficiency measures in terms of lighting upgrades, upgrades of the heating, ventilation and air conditioning systems and their controls, so the building management systems, upgrades to the refrigeration system, which as you can imagine in a supermarket forms a very large part of their total energy consumption. They looked at heat recovery and solar PV. So if you only look at the energy efficiency measures alone, that package of measures would result in an 11.8-year payback period, which is quite typical of normal energy performance contracts, which typically run between 5 and 15 years in duration. What they also did was they talked to an aggregator partner, a demand response aggregator, who looked at the systems that were available on the supermarket site and identified a number of flexibility programs that the supermarket could participate in. And what we discovered on undertaking that analysis is that through a combination of using the HVAC systems, the flexibility in the refrigeration systems, the on-site generator, PV system plus battery storage, that could result in a payment to the building owner through flexibility of an additional €32,000 per year. Now what that does is it reduces the overall project payback period to 9.8 years, which is around a 16% improvement on the initial 11.8-year payback. So in short, considering demand response alongside your energy efficiency measures can take a project that's marginal and that might not be funded, it can turn it into a project that's viable. So why would Escos and aggregators work together? I'm going to take a look at whether there are common or conflicting interests between Escos and aggregators. Now, you might think that they have conflicting interests because an Esco's purpose is to reduce building energy consumption. So if you take a look at the original load of a building before any energy efficiency measures, you can see that the flexibility potential might be considered greater in the original scenario compared to after the energy efficiency measures had been implemented. But of course, what this doesn't take into account is that when you upgrade a building with energy efficiency measures, you typically also upgrade its smartness, as I've mentioned before, through upgrades to the building management system or through new technologies that weren't available before, like renewable energy systems with battery storage potential. So although it seems like there are conflicting interests, there are actually also a number of common interests. So one of them is access to that potential flexibility that wasn't there before. But there are also many other benefits. And these can include access to new and untapped markets. So it's quite common for Escos and aggregators to work in very different markets. Escos often go for public sector clients or large hotel groups, supermarket groups, whereas traditionally an aggregator would look more at large industrial clients with easily controllable loads. So there's a potential for a unique selling point there and differentiation in a crowded or a growing market by being able to offer something that your competitors don't. There's a value add for clients in terms of being able to access both revenue streams with less contractual complexity. From the Esco's perspective, it means that their energy performance contract could be shorter in duration because of the additional revenues that are generated from demand-side response. And from the aggregator's perspective, working with an Esco can reduce their cost of sale. If you imagine how much effort it takes to persuade a building owner to participate in a flexibility program when it's something that perhaps they don't quite understand or they've not really come across before, it can take a long time. Whereas an Esco may already be a trusted partner for that building owner because they've already handled some energy efficiency measures. And so it might be much easier for the aggregator to make a sale via an Esco who already has very good relationships with their existing clients. From the building owner's perspective, there are additional benefits other than just the revenues generated. Smart buildings tend to have a greater value, and occupants tend to be more comfortable because the building is more controllable, which leads to additional health and well-being of staff, and potentially even a improved brand image for the company. So the common interest for the Escos and the aggregators are that both aim really to maximise the revenues that are available from building energy assets, and they could work very well together. And indeed, that's what we found with the Novice project. The benefits for both parties outweigh the risks. Coming to my last slide now, the key messages really that I'd like you to take away from this presentation are that business models that accelerate the uptake of flexibility services and these innovative flexibility solutions that you've been hearing about this afternoon are really needed, and they shouldn't be overlooked. Novice that I've presented this afternoon is one option, but there are many others out there. You might hear about one or two more this afternoon, but don't neglect to think about the business model for how you get these new solutions into the market. Novice has shown that combining energy efficiency with flexibility can improve the business case for a whole building retrofit project. And that's really important because we've had the details about the renovation wave from the European Commission recently, and we know that building renovation rates really need to increase rapidly over the next few years if we have any chance of meeting our energy efficiency and carbon reduction targets. And finally, just a note to say that Escos and demand response aggregators should consider working together. It could differentiate themselves in the market, and I think that those that are willing and ready to take that step could have an advantage over their competitors. So that's it from me. Thank you very much for listening, and I'm happy to take any questions.
Thanks, Joe. Great presentation. I'm really glad you brought up the business models because after Apostolos, I want to ask you about that. That's my expertise. So I'm glad you brought that up. Very succinct and informative. Thank you.
No problem.
Okay, so next we shall move on to Jesse Glicker from BPIE, which is the Buildings Performance Institute of Europe. And Jesse will be presenting the AmBIENCe project. Jesse, it's all yours.
Great. So let me just make sure that I've got the settings right here. Okay, terrific. Hi, good evening. I'll be very aware of time. I'll try to move quickly without speaking too fast. But I've updated my slides a bit to be a bit shorter so we can keep to time and still have some space at the end for questions. So hi, everyone. I'm Jesse Glicker from BPIE. I'll be presenting the AmBIENCe project. So yes, we're very happy to be part of this. And it's really good that we're following Joe's presentation because AmBIENCe is also, again, talking about Escos and business models. So it's another solution really integrating energy efficiency solutions with demand response. So I think it dovetails nicely. We're in our first year of the project, just wrapping up our first year of the project. So we're at a bit of a different stage. So it fits in nicely with some of the solutions we've heard before, but in particular the business case model. So yep, as I mentioned, we're entering our second year. We've got consortium partners sort of evenly spread throughout the EU. And later when I talk about our pilot projects, I'll get a little bit more into where our pilot projects are and how we're piloting the AmBIENCe solution. So just a little bit about our vision and our mission with the AmBIENCe project. With advances in different technological fields, such as the Internet of Things, sensorization equipment, and automated control devices, AmBIENCe aims to go beyond the passive building concept by adapting an active control approach, using buildings' inherent flexibility to further reduce the losses or costs and maximize the use of self-generated energy, and then offer services to the grid and market stakeholders. So really integrating these different, or the inherent flexibility of buildings, so really making buildings smarter. So our vision and our mission is working with electrification and carbon intensity of electricity to really reduce carbon emissions and electricity usage within a building. So AmBIENCe is using energy performance contracting to actively manage buildings. The idea is to include demand response into the model and valorize the flexibility that is available. We're in the phase of developing the business model. So we're currently working on the business model. Up until this point, we've really been doing a lot of analysis, which I'll discuss in a moment. We've been conducting an analysis of our consortium partner countries, but also the EU at large, to see how developed the market is and what regulatory boundaries or what regulatory barriers there are in place for implementing or including demand response. So just a bit about the beneficiaries of the project. So we've, of course, the environment and society as a whole as the main objective here. Consumers and energy system stakeholders, and then Escos as well. So a bit about our methodology, and this is really fits nicely with what Joe was saying. So we've got the traditional EPC model here, and then you can see the AmBIENCe active EPC concept in the middle, and in yellow, they're the additional elements that are enhancing the traditional EPC, so including flexibility and what that would look like and how that would enhance the traditional energy performance contracting model. So a bit about our work packages and timeline, and I'll go quickly because this is less interesting and can all be found on the site. So as I mentioned, we're in the middle phase, so work package 3 here, and work package 2, developing the business model and implementation and validation of the active EPC concept with our pilot projects. And our timeline, like most Horizon 2020 projects, we have been extended by 6 months, so giving us a bit more time to implement and work with the pilot projects. So we're in this phase right now. So a bit about our project, a bit about our pilots. We've got one that is an office building in Porto, in Portugal, and one that is an office building in Brussels. So both office buildings to test the solution. So as I mentioned, what we've been doing to date is a lot of market analysis and the regulatory analysis. So I'll just present a couple of our findings. The full report, which is quite long, I think it's about 120, 130 pages, can be found on the website, the AmBIENCe website. It is incredibly interesting and does provide a lot of insight specifically into the countries we did a deep dive into, which were Spain, Portugal, Belgium, and Italy. So I'll talk a bit about them. So the analysis of the current directives, policies, and measures that are relevant for the active EPC concept was really what we focused on here to figure out best practices and really what recommendations we would pose to change the barriers to current implementation of the active EPC concept. So first we did an overview of the energy performance contracting and Esco status at the member state level. So here you can see on the left our analysis based on the 4 countries I mentioned before, or 5 countries, excuse me, Spain was included, I left that out. And then also the whole member state level one that we had a look at. So the assessment of the status of the EPC's Esco market was conducted based on the following factors: Esco market longevity, the relative size of the Esco market growth, and the EPC market value, and the implementation of EPCs in various building sectors. Because one of the things we really wanted to focus on is what sectors this EPC business model would be appropriate for. So we found, as you can see by the color coding, Italy was, of the consortium partners, Italy was the most advanced country. The Esco market in Italy is considered to be one of the oldest and the most developed in Europe, which is mainly due to strong legislation and standards established in Italy for energy performance, for energy efficiency in buildings. Italy was followed by Belgium, where the energy service market is considered stable and moderately sized, and then Spain, where the energy service market has been sort of awaiting a boom. There's a lot of very good, there's very good framework there, but it still needs that extra push. But there have been in recent years a complex set of governmental support measures. And then finally, there's Portugal. It has the lowest score for the key areas investigated. The Esco sector in Portugal is currently considered underdeveloped and relatively small. So given our look at these 5 main markets, it was really useful to sort of see from developed to least developed, and see where solutions can be in place and what different recommendations we would give depending on Esco market maturity. So then we also did a status of the demand response services offered by buildings at the member state level. So again, you can see what we've done on the consortium level, and you can see what we've done on the member state level. So this assessment was based on demand response cases, access to the market, service providers' access to the market, product requirements, and measurement and verification procedures. So again, just to quickly go through the consortium scores, Belgium was the most advanced country in the consortium. Over the past several years, the Belgian transmission grid operator created a new framework to enable participation of new energy sources, such as demand flexibility, with new types of market players, such as aggregators. While the implementation of the framework is still ongoing, the end goal is to open up the different products and services to all technologies, demand-side management, storage, things like that, independently of the connection to the TSO or DSO and the type of provider. So that was very enlightening for us to have a look at that. And again, Portugal was sort of Spain and Portugal together, so it sort of needed quite a bit more push when it came to regulatory measures, or sort of an assessment of the regulatory measures happening at the national level to open it up to demand response. And that brings us to the end.
Wow, what a great market analysis, Jessie. That is fantastic.
Thank you.
I'm so glad you presented that. I have to say that I'm going to use those in several deliverables.
Great.
I hope
sorry.
Yeah, go ahead, please.
I highly recommend checking out the deliverable. There's also on the website, there are fact sheets that give a very good recap of the individual consortium countries that were looked at. So they might be a good source for information as well.
Yeah, it's a common practice to assess the readiness of the partner countries. And so you did a really great job on that. Congratulations.
Thank you.
All right, wonderful, thanks. So last but certainly not least, before we head to the panel session, I do want to make sure that people leave on time if they need to, and we're perfectly on time. So thank you everybody for respecting that. Really appreciate it. So last up, Delta Project. Speaking for the Delta Project will be Apostolos Solakis, hopefully I pronounced that correctly, from the Center for Research and Technology in Hellas. Take it away, sir.
Thank you very much. Good afternoon to everybody. I'm Apostolos Solakis, and I will be presenting Delta. I'll try to be brief. Delta is a research and innovation action which lasts for 3 years. We are currently on our 3rd year. The budget a little bit lower than 4 million, 10 partners from 8 countries for the consortium, and we have an aggregator from UK and a DSO from Cyprus. I will not go too deep into the rationale and the motivation. The idea is to untap the flexibility through demand response services, just like other projects in this afternoon session. However, our focus is to present a different distribution structure that focuses on small and medium customers through a novel, secure demand response management platform. In order to deliver that, we wanted to ease the computational effort of the aggregators, which is the main focus of our project, by distributing the intelligence required for demand response at the energy markets. Also, we try to engage prosumers with added value services that have to do with collaboration, incentivization, and gamification. And we try to promote interoperability by adopting the OpenADR standard for all communications through one of the ontologies that we have developed based on the OpenADR standards. And of course, as discussed before, we have some new business models and recommendations for policymakers in order to be able to adopt these services that we are delivering into the markets as soon as possible. Here you can see our concept in a graphic representation. So instead of the centralized approach that's currently in the smart grid, where the aggregators have access to each customer specifically, we are trying to relieve aggregators from these resource-intensive tasks by introducing the Delta virtual node and the fog-enabled intelligent device at customer side. So we explore the virtual power plants principles in order to present to the aggregator large entities that can participate to the energy market as they are right now, but aggregating small and medium customers together to be able to present that without needing the aggregator to handle each customer one by one. Of course, we are also trying to simplify and fortify the contractual agreements, not only by providing enhanced security through the Delta blockchain, but also with smart contracts. So every transaction is automated through a smart contract over the Delta blockchain. And of course, we have other key enablers like the collaboration platform, the award-enabled services, and enhanced visualization aspects for the customers. The impact that the project has mainly focused on interconnecting the energy stakeholders at all layers to provide stable and secure increase of renewable energy source penetration by better handling all assets regardless of their size. Affect ongoing policy developments either at standardization bodies or at EU and national policy making. Bring greater energy security, sustainability, and competitiveness by new services and new business model. And the most important thing is to provide access to modern, specifically small prosumers. We have 3 pilot sites, 1 small pre-pilot at Greece and 2 large pilot sites at UK and University of Cyprus. And we divide our work in 3 layers, starting with a Delta customer, which is the most important aspect. We have designed a hybrid device, both in terms of hardware and software, which is a novel, powerful toolkit that empowers small and medium customers to participate in TR programs. We have enhanced security with an embedded DPM module. We have direct communication with various wired and wireless protocols, and of course interfaces for smart meters, building and energy management systems. And of course, as said, we are OpenADR compliant. You can see here the new device. On this device, we are running a series of lightweight software engines, starting with load and PV forecasting. We also have a new approach for flexibility estimation. We combine unsupervised and supervised models in order to be able to extract the flexibility potential of a customer from a central point of measurement without getting into more detail on asset level. And of course, by having all of that information, we are able to deploy and optimize self-consumption logic that combines all available assets without the aggregator having knowledge over it, and of course, maximizing both financial and comfort objectives from the customer side. Getting all of that information reported to a higher level, a virtual node that follows the virtual power plant principles. We have a multi-agent framework that provides a highly robust ER management. There's an internal clustering feature that uses flexibility, availability, reliability, and other metrics in order to efficiently find the most appropriate customers to handle a DR request from higher levels. We perform a cross-validation on all forecasting through individual and aggregated results. So we get the individual results, and based on other algorithms that are executed in aggregated level, we are cross-validating the results. So we can report to the aggregator a result that is as close as possible to the actual thing. And of course, we have an intelligent optimal dispatch and fail-safe mechanism to ensure TR success within each virtual node. This is quite interesting because, first of all, we introduce flexibility as a virtual distributed energy resource. So imagine all optimization schemes that are applied on DERs that can use now flexibility as one of them. So we use that to test the various optimization schemes for DERs in the literature. And also we introduced two fail-safe mechanisms, one intra and one inter-DVN communication in real-time operations, so that we can identify when a DR is going to fail because one of the customers cannot deliver what has been requested. We quickly find other customers that have the flexibility and are available at that time to deliver that amount with explicit DR requests, in order to get that either within the same node or to other nodes that fill in certain constraints. Going to the last layer, which is the aggregator, we try to keep the role of the aggregator as it is right now with added value services. We have an efficient, automated, and dynamic aggregation of small and medium customers. We practically create the DVNs and we adapt them over time based on historical data as well as contractual data. As you can imagine, we can handle also large customers as is, because one DVN is assigned to one customer, and this facilitates things because we don't have to run two engines at the same time. We have two engines for price forecasting, which we have developed and we are trying. We have the intraday and the imbalance markets, based on which we are trying to bid and identify how we can maximize the aggregator's revenue. We have an unobtrusive collaboration with DSOs for ensuring grid stability. So we have a grid topology which runs on an external simulation platform when we execute different scenarios every time we have a DR request to see whether it can be a threat to the stability of the grid. We also have a dynamic optimization based on spatiotemporal characteristics, DVN reliability, and fairness. And finally, on the aggregators level, we apply the gamification collaboration services in order to maximize end user engagement and DR success again. So we have demand response games, we have collaboration games, we have identified vouchers that can be given based on the points that they have earned from the gamification process in order to keep the prosumers active, because we have to gain as much as possible from their flexibility. As horizontal services, we have the Delta permission blockchain. It is based on hardware ledger fabric, and all information that is related to demand response is stored on the blockchain. And also we have the smart contracts on top of that, which have integrated all OpenADR services in order to be able to handle automatically all transactions. So as soon as a DR request is serviced to either of the layers, a smart contract is created, and either if it is rejected or failed or successful, everything is handled automatically by the engine on the back end. So as you can see, I try to make it as brief as possible to give more time for questions. Delta envisions to harness the untapped potential of small and medium customers by providing a framework that can automate, but also secure and to make more efficient demand response management, while also creating added value services that can enrich the experience for the end users, raising their engagement and providing, let's say, more interesting approaches for them to actually participate in NPR requests. And through all of that, we introduce new business models and revenue streams for all involved stakeholders, starting not only from the aggregator, but also from higher levels up to the small customer. In particular, our business models will be present and will be introduced in one of our webinars, where we expect to have, we will have speakers from both EU and US stakeholders, and we will be presenting market perspective and business opportunities for demand response in Europe. It's on the 19th of November, and we would like to see you all there to continue the discussion over the business opportunities of demand response. I hope it was brief to give more time for discussion. Thank you all, and if you have any questions, I would be delighted to answer them.
Zia, are you talking? Maybe you are unmuted. I'm not hearing you very well. Zia will take the lead to make the conclusion in a minute.
Okay, well, maybe, I guess, luckily we had the technical difficulties at the end, but maybe we could say goodbye unless there are any final questions, but I don't see any in the chat box.
No, I see neither no new question. Zia wanted to make some conclusion and ask all the panelists if you have some conclusion and new ideas on topic, but yeah, as the time is running and as you have that technical issue, if nobody have something to add.
No, thanks.
Hello?
Okay, yes, yeah, you're
okay. Sorry about that. I lost my sound. I apologize, everybody. Thank you, Apostolos. There is one question, or maybe two questions. Let's see here. Okay. Ooh, several questions. Let's see. No. Okay. What is the main benefits of open ADR according to you? And that's for Apostolos.
Well, to start with, we have a formal way of actually translating the information required for demand response signals. And through the Delta framework, we actually created the OpenADR ontology in order to also support semantic interoperability. So we took the standard, we created the ontology, and we are now practically using both with main focus on the ontology part, in order to be able to handle more efficiently the, let's say, machine-to-machine information exchange within the framework, and of course with third party. As you know, I don't know if you're referring to the OpenEDR specifically or to common frameworks and standards for exchanging information. However, there is quite a limitation in terms of standards for demand response. Even OpenEDR has some let's say, limitations that we are currently trying to identify and present with our communication with the Alliance. We know that they are also working in order to present merits and a new framework as well. So towards interoperable systems, it is good to work on one framework which should be adopted by everybody in order to facilitate things instead of working with a lot of different protocols.
Okay, thank you. My webcam doesn't seem to be working, and I think that instead of having a panel, I think we might as well just close here, and then we can follow up. So there'll be a post-workshop survey for the attendees who will receive it via email. And we hope that you answer that and look more into the projects that have participated today. We appreciate everyone's support of the conference and of this workshop. We hope you enjoyed it, and I think we'll close here. So thank you, everybody, and have a wonderful evening, and enjoy the last day of the conference tomorrow.
Thank you. Bye.
Good
Thank you,
night.
Zia. Bye.
Thanks so much.
Thank you very much.
Thank you. Goodbye.
Thank you. Bye-bye.